Here is a list of powers of 3. What is the remainder when I add all of these up and I divide by 7? This is a question which you may have seen before, this kind of question of looking at remainders when I take powers of a number modulo another one. And usually you are used to seeing some sort of a cycle. Actually, these numbers are chosen very carefully so that we can see a rather beautiful cycle. What I'm going to do is this. I'm going to start with 3 to the 0, which is 1. And now what I'm going to do is I'm going to draw a pattern which says what happens when I keep multiplying by 3 if I care about the remainder when I divide by 7. 3 to the 1 is 3. So far, there's no big deal here. But what I'm going to do is I'm already going to draw the possible remainders when I divide by 7 here. 1, 2, 3, 4, 5, 6. I'm not writing 0 because I'm taking powers of 3 and I'll never get a remainder of 0 when I divide by 7. But since I have the 1 and the 3, what I'll draw here is that from the 1, I go to the 3 if I multiply by 3. What is 3 squared? 3 squared is 9. So 9 has a remainder of 2 when I divide by 7. And so I'm going to draw my arrow here. 3 goes to 2. Next, what I'll say is that 3 cubed is going to be, I'll already use the 2, take 2 times 3 to get 6. And so now I'll draw the arrow from the 2 to the 6. I will continue in this way. From the 6, that would be 3 to the power 4. It will be congruent to 6 times 3, which is 18. But 18, when I divide by 7, is going to be 4, because 7 times 2 is 14, and the remainder is then 4. So I will then connect the 6 to the 4. Next, I do 3 to the power 5 is congruent to 4 times 3, which is 12, which is going to give me 5 when I divide by 7. And that will connect to here. 3 to the 6 is going to be 5 times 3, which is 15, which is 1 when I divide by 7. So this 5 goes back to the 1. But this is interesting. You see, I already know what happens if I take the 1 times 3. So what I just found out is that all of these go around in a circle, and I use up every single possible remainder when I divide by 7. I'll say I chose those numbers on purpose, because if you take a class on number theory, what this actually means in a number theory terminology is that 3 is a primitive root modulo 7. Primitive root means that if I keep multiplying by 3, I go through all of them. Well, now what was the question asking me to do? The question was asking me to add up these powers. Whenever I can add up all of these, modulo a prime like 7, something nice happens. Because I already see that my first 6 numbers that I'm doing here, every 6 consecutive numbers, are just going to be all 6 of these added together. So what is all of 6 of these added together? This is just the sum of 6 consecutive numbers from 1 to 6. So it's the first plus the last, the average basically, the first average of the first and the last, times how many there are, which is going to be 7 times 6 divided by 2, which is 21. There's an important fact here. This is always going to be divisible by the 7 because 7 is prime. So here I chose 7 as a prime. And so what happens here is that this prime, 1 plus 6, is actually never going to be cancelled by the thing underneath. That's actually important. This is congruent to 0 modulo 7. So all that's left is to figure out how many terms there are and to remember that every 6 of them will get a sum which is 0 modulo 7. The number of terms is from 0 to 1997, and so I will have 1998 terms. Now, if I want to see how many 6s there are, I want to take 1998 divided by 6 and look at what the remainder is. Actually, these numbers were chosen carefully. 1998 is even. And actually, if I add up 1 and 8, it's 9. So the sum of the digits is divisible by 3. So what this actually means is that this number is actually a multiple of 6. Oh, but I specifically had chosen numbers so that what I would end up having is every 6 adding up to 0 mod 7. I have a multiple of 6 many terms, and so the answer to the entire question, what the remainder is just 0. Everything cancels. I chose this to review a little bit of what you may already have known of the way to do that the way to do this is to write these powers of 3 and look for when they repeat. But I also did this to show you this nice pattern. It is not always true that when you take a number and multiply by something, it goes all the way around. For example, if I had not been doing powers of 3, but I'd been doing powers of 6, my picture would look very different. From 6 to the 0, it's 1. 6 to the 1 is 6. But 6 squared is 36, which is 35 plus 1, and you'd go right back there. So this is not always true that you go through all of the remainders modulo the prime. The last thing I want to say is that there is another way to do this problem, but in this case it's actually more complicated, so I won't go deep into it, other than saying it's possible. The other way is to say that this is a geometric series. And if you have a geometric series, you can write this as just a ratio of 3 to the power 1998 minus 1 divided by 2 minus 1. And with that, 3 to the 1998 minus 1 divided by 3 minus 1. And with that, you can also find what the remainder is when you divide by 7. Although that one you need to be a bit careful to know what happens when I divide by 2 modulo 7. And for that, it is actually still useful to look at this picture, because for this picture, we know what the inverse of 2 is. I will say that there's actually another way to do this problem, but in this particular case, it's actually more complicated than what we have here. So I won't go into greater detail, other than saying that here you have a geometric series. And so there's a formula for the sum of this geometric series, which is just 3 to the power 1998 minus 3 to the minus 1 divided by 3 minus 1. So I could instead say that this whole sum is this, and try to see what is the remainder when this is divided by 7. The slight complication is that I would also have to deal with how do I divide by 2 modulo 7. And what that means is we need to know what times 2 is 1 modulo 7. A little bit more complicated. The answer to that is 4, because 4 times 2 is 8. But this other way, I would say, is a method that's better used for those who maybe have more experience in a number theory course. In the end, the goal of this question was to finish the AMC 10, but at the same time, also have a chance to introduce to one of these nice arithmetic coincidences of the primitive root modulo 7, which is 3.